the 1970s, astronomers began carefully measuring how fast stars orbit inside spiral galaxies. The expectation was straightforward. Stars near the center, where most of the visible mass is concentrated, should move quickly. Stars farther out, where less visible matter exists, should slow down. This is how gravity works. But when astronomers measured the actual rotation speeds, something strange appeared. The outer stars were not slowing down. They were moving almost as fast as stars near the center. According to Newtonian physics, this should not happen. If only the visible matter were present, the outer regions should not have enough gravity to hold those fast-moving stars in orbit. Yet the galaxies were stable. They were not flying apart. The data kept repeating the same result across different telescopes and different galaxies. The conclusion was unavoidable. Either gravity behaves differently on galactic scales, or there is far more mass present than we can see. Astronomers chose to trust the measurements. And that decision opened one of the most profound mysteries in modern cosmology. The equations of motion were not ambiguous. If stars were orbiting at those speeds, the galaxy must contain more mass than was visible in stars and gas. That unseen mass had to extend far beyond the luminous disk. Astronomers began modeling galaxies surrounded by enormous invisible halos, spherical regions of matter stretching well beyond the visible edge. These halos did not emit light. They did not absorb light. They did not reflect light. But they exerted gravity. This was the birth of the term dark matter. At this stage, dark matter was not a particle or a detailed theory. It was a placeholder, a recognition that the universe contains mass that does not interact with light. And the more galaxies astronomers studied, the clearer the pattern became. Flat rotation curves were not rare. They were universal. If dark matter existed only in galaxies, it might have been dismissed as a modeling issue. But galaxy clusters told the same story, at an even larger scale. Clusters contain hundreds or thousands of galaxies bound together by gravity. By measuring how fast galaxies moved inside these clusters, astronomers could estimate total mass. The results were extreme. The visible matter, stars and hot gas, accounted for only a fraction of the required mass. Without additional unseen mass, the clusters should have dispersed long ago. Yet they remained gravitationally bound. The discrepancy was not small. In some clusters, visible matter represented less than 20% of the total mass needed to explain the motions. Dark matter was no longer optional. It was required to explain structure on cosmic scales. The most dramatic confirmation came from Einstein's theory of general relativity. Mass bends spacetime, and bent spacetime bends light. Astronomers observed distant galaxies positioned behind massive galaxy clusters. Instead of appearing in their true positions, their light was distorted, stretched into arcs and rings. This phenomenon is called gravitational lensing. By measuring how much the light bent, scientists could calculate how much mass was present in the cluster. The result was unmistakable. The bending required far more mass than was visible. In some cases, detailed lensing maps showed mass concentrations where almost no luminous matter existed. Light was being bent by something invisible. Dark matter was no longer just inferred from motion. It was mapped through gravity itself. Dark matter does not emit light. It does not reflect light. It does not absorb light in a detectable way. So humanity had to measure it indirectly. The key tool became gravitational lensing, not the dramatic arcs seen in massive clusters, but something far subtler. Weak gravitational lensing. When light from distant galaxies travels across billions of light years, it passes through regions filled with dark matter. The mass slightly distorts the shape of those background galaxies. The distortion is tiny, often less than 1%. No single galaxy reveals the effect clearly. But by analyzing millions of galaxies statistically, astronomers can detect patterns in those distortions. From those patterns, they reconstruct a map of mass distribution across vast regions of the universe. In other words, humanity does not see dark matter. It sees how dark matter bends the light of everything else. That bending is enough. To measure weak lensing accurately, astronomers need two things: precision and scale. The distortions are so small that even atmospheric turbulence can overwhelm them. That is why space telescopes became critical. One of the newest instruments built specifically for this purpose is Euclid. Euclid was designed to map billions of galaxies across more than 1/3 of the sky. Its goal is not to look at individual objects, but to detect patterns and structure. By measuring galaxy shapes and distances with extraordinary precision, Euclid constructs three-dimensional maps of dark matter distribution. From these maps, scientists can study how structure formed over cosmic time. Dark matter is not randomly scattered. It forms a web, filaments connecting clusters across the universe. Euclid is not discovering dark matter directly. It is mapping its gravitational fingerprint. Observations alone are not enough. To understand dark matter, scientists also simulate it. Using supercomputers, researchers model billions of particles interacting under gravity. These simulations show how dark matter collapses into halos and filaments over billions of years. When compared with real sky surveys, the results match strikingly well. Galaxies form at the intersections of dark matter filaments. Clusters sit at dense nodes of the cosmic web. Without dark matter in simulations, the universe we observe cannot be reproduced. This alignment between observation and simulation strengthens the case. Dark matter is not a convenient patch. It is embedded in the large-scale architecture of the universe. Dark matter does more than hold galaxies together. It drives cosmic evolution. By comparing maps of structure at different distances, and therefore different times in cosmic history, astronomers can track how quickly matter clumped together. This growth rate is sensitive to fundamental physics, including the nature of dark matter and dark energy. If dark matter behaved differently, structure formation would look different. Surveys like Euclid allow scientists to test these models with precision. Humanity is not simply observing the universe. It is measuring its evolution. Dark matter is still invisible, but its effects are now mapped across billions of light-years and billions of years. What began as a rotational anomaly is now one of the central pillars of cosmology. Dark matter does not interact with light. That much is clear. But it does interact gravitationally, and that narrows the possibilities. It cannot be ordinary matter that simply emits very little light. Astronomers have already measured how much normal matter exists in the universe, using observations of the early universe and the abundance of light elements. Dark matter must be something else. The leading idea for decades has been that dark matter consists of new, undiscovered particles. These particles would interact very weakly with normal matter, passing through stars, planets, and even our own bodies without noticeable effect. One popular class of candidates has been called WIMPs, weakly interacting massive particles. If WIMPs exist, they would have mass. They would exert gravity, but they would almost never collide with ordinary particles. This makes them extremely difficult to detect. And yet, humanity has built experiments specifically designed to catch one rare interaction: a tiny collision between a dark matter particle and an atomic nucleus. The search is not theoretical anymore. It is experimental. To detect dark matter directly, scientists had to eliminate almost all background noise. That is why major detection experiments are built deep underground, beneath mountains or inside mines, shielded from cosmic radiation. Inside these facilities are enormous tanks filled with ultra-pure materials, often liquid xenon. These detectors are designed to register even the faintest flash of light or electrical signal caused by a particle interaction. If a dark matter particle collides with an atomic nucleus, it should produce a tiny burst of energy. So far, no confirmed detection has been made. But the sensitivity of these experiments has improved dramatically over the past 2 decades. Each new generation of detectors reduces background interference and increases detection volume. Humanity is not waiting for the universe to announce dark matter. It is building instruments quiet enough to hear a whisper. Another approach is to try to create dark matter in the laboratory. At facilities like the Large Hadron Collider, particles are smashed together at extremely high energies. These collisions can produce new particles, sometimes ones never seen before. If dark matter particles are created in such collisions, they would not be detected directly. Instead, scientists would notice missing energy and momentum, signs that invisible particles escape the detector. So far, no definitive signal of dark matter has emerged from collider experiments. But the search continues. The absence of detection is itself informative. It helps narrow down the range of possible particle properties. Humanity is testing the idea of dark matter from both directions, waiting for it to arrive from space, and trying to create it on Earth. Despite decades of effort, dark matter remains undetected in the laboratory. This does not weaken the evidence for its gravitational effects. The astrophysical data are overwhelming, but it leaves open a possibility. Our assumptions about its nature may be incomplete. Some scientists propose lighter particles, such as axions. Others explore modifications to gravity itself, though these alternatives struggle to explain all observations consistently. New experiments are being designed to test these possibilities. Future detectors will be larger, colder, quieter. Meanwhile, space missions like Euclid continue refining maps of dark matter's distribution. The invisible structure of the universe is now measured with precision. What remains unknown is its fundamental identity. Dark matter is not a speculation anymore. It is a measured component of the cosmos. Humanity has mapped where it is. Now it is trying to learn what it is.